Hello, this is Mr. Gilmore with the 1.5 Algebraic Postulates. Before we jump into this lesson today, I do want to make a quick note that this is the last lesson of Chapter 1, which means we have a test coming up. What this also means is that there will be a review sheet that you should be checking out also on Canvas. So, with that, let's take a look at what the algebraic postulates are. The very first one is what's known as the reflexivity of equality. Now, when we jump into geometry, we will realize that yes, there is some overlap with some algebra concepts because we're going to need to use those algebra concepts in order to progress logically through some proofs. Now, if we take a look at the reflexivity of equality, this is a postulate. This is something that's very obvious. Remember, that's what postulates mean. It's a basic fact. It's a basic assumption that people have arrived to without needing any sort of justification. So the very first one we encounter just simply says that for all x, x is equal to x. In plain English, we're really saying that every quantity is equal to itself. So examples, 1 is equal to 1, measure of angle ABC is equal to measure of angle BC, Aristotle is equal to Aristotle. So if I want to declare, let's say, a segment measure equal to itself, I can justify that, and it really is obvious, right? It's one of those basic facts that I can just justify it using the reflexivity property of equality. There's also transitivity. You may have actually used this transitive property in the past. How we read this in terms of our algebraic postulate is that if we're given any quantities x, y, and z, and if we know x is equal to y and y is equal to z, then x is equal to z. Now, I'm going to take Euclid's formulation, which I prefer to use when he talked about his transitivity of equality. And what he said was things that are equal to the same thing are equal to one another. Which another way then I could read that top sentence would be if x is equal to y and z is equal to y. Notice that I just reversed the order of that second equation. So if x is equal to y and z is equal to y, that means x and z are both equal to the same thing. That means they are equal to each other. And so that's one, we will use the transitivity of equality quite often when we encounter many of our relationships here in geometry. We also have substitution, the substitution property. The substitution property works slightly different than the transitivity property. However, you will see that there are some cases where we can interchange the two, where either or transitivity or substitution may apply as the justification. But there is a distinction between them, and we're going to make note of that distinction in the next slide. Let's take a look then at what substitution says. It says that if x is equal to y, so we've got this quantity x is equal to some quantity y. That means whenever I encounter an expression that has the value of x in it, or that quantity x in it, I may replace that x with the value of y, and vice versa. If I encounter the y anywhere, I may replace the y with the value of x. So if Aristotle is equal to Plato's teacher, and Aristotle is the first great logician, then I can take out the word Aristotle and replace it with Plato's teacher, thus saying then Plato's teacher is the first great logician. So we're going to see that with substitution, you're merely replacing. You're not actually creating any new sort of relationship. You're merely just equality. You're just merely just replacing within an equality. So let's take a look at the difference between transitivity and substitution. So in part A, we're looking at the transitivity property. Measure of angle A equals measure of angle B, and measure of angle B equals measure of angle C. Then I can justify that angle A is equal to angle C. Could I, actually in number one there, I can justify that using transitivity. But could I have also justified that using substitution? Yes, merely what that says is I can replace or substitute angle A in for angle B, or replace angle B with angle A, and then I have my conclusion. Let's look at number 2 then. Angle A is right. Measure of angle A equals measure of angle B, thus angle B is right. What have I done there? I've merely replaced. Notice that there's only one equation or one equal sign in the second statement. So in the second one, that would be justified using substitution only. I cannot justify statement 2 using transitivity. Transitivity is taking where I have two equalities and creating a third, where in substitution, I'm taking one equality and merely replacing one of those quantities with another. So that's really the comparison, the compare and contrast of the transitivity property and our substitution property. So be very careful with those. If it feels more like transitivity, then I use transitivity. But if I know I'm merely replacing, then I'll justify that with substitution. Now, whenever we encounter, let's say, expressions that become simplified, and you've seen those many, many times in Algebra 1 and even in the past before Algebra 1, where you just simplify an expression, where you either add like terms or you get common values together. Whenever you simplify, we use the substitution property as our justification. There's an example down here below where I have this equation, 2x plus 3x equals 12. Well, then if I were to replace 2x plus 3x, because I know it's equal to 5x, that really what I'm doing is I'm replacing 2x plus 3x with the 5x. That's substitution. So every time you simplify something, you are using substitution. Now, we got to be careful with substitution then in terms of some of our other algebraic postulates as well, because if I'm only simplifying one side of the equation, that's just substitution. However, we do have some other postulates where we affect both sides of the equation, such as the addition property. Addition property simply says that I may add equals to equals, right? So if I have x plus y and a equals, or sorry, if I have x equals y and a equals b, then I may add those equals to equals. So x plus a has got to be equal to y plus b. I'm going to steal this from Euclid's formulation, which is equals added to equals are equal, okay? Equals added to equals are equal. So is x and y equal? Yes. Is a and b equal? Yes. If I add those equals to equal, will they be equal? Yes. All right. So you may affect both sides of the equation with the same quantity, with equal quantities, I should say, and then you get an equal result. With addition comes subtraction. I may then take equals from equals. So equals subtracted from equals leaves equals, or equals taken from equals yields equals. So if a and b are equal and x and y are equal, then I can take a away from x and b away from y for any quantities x, y, or a, and I will then yield equal results. So we have the subtraction property, right? These are all basic assumptions, basic facts that we're arriving to within our geometrical system. We also have multiplication and division. Multiplication, right? If I know that a is equal to b and x equals y, then I may multiply those equals and get equals, right? So equals multiplied by equals yields equals, or will result in equals. With division, there's one case we have to avoid, and that is the division of 0. So if I give you a is equal to b and x equal to y, I also must tell you that whatever quantity we're dividing by cannot equal 0. So we're going to divide by a, which means I cannot let a equal 0, which means b inherently is also not equal to 0. So then what results is x divided by a is equal to y divided by b. So equals divided by equals are equal. And you will see that we will occasionally use multiplication and division property here and there. It does not get used as often as our addition and subtraction properties. But in case we need these laying around, we have them. We have the multiplication division postulates, algebraic postulates laying around. Here's a distribution property. We've seen this one in Algebra 1, where if you have a sum, right, of two quantities and you want to find the product of that sum, you may then distribute that product through to each of the sum. So the product of the sum is then also equal to the individual products summed. And so for any values of a, b, and c, we take a look that if a is times the sum of those two quantities b and c, then I may then find the product of each and then sum them together. So a times b plus a times c will result in the same yield. And we don't see distribution property as often, but you will see it come up here and there, and it will be quite handy to have that laying around. The last one is known as the law of trichotomy. Okay, what the law of trichotomy states is that for any values of a and b, three things must be true, or three things, I should say one and only one, precisely one of these three things will be true about those two quantities a and b. Either a will be equal to b, a will be less than b, or a will be greater than b. That's what's known as the law of trichotomy. Why do they call it the law? Well, it's just actually at this point, it's kind of just tradition. Okay, traditionally we just call this the law of trichotomy. What it really means is the relationship that any quantities can hold in mathematics, and this relationship means they can only hold precisely one of these. Right? A is either going to be equal, A is going to be less than, or A is going to be greater than. Never will we see A be equal to and less than. Now you may be asking, what about this symbol less than or equal to, or greater than or equal to. Well, notice what vocabulary I'm using. I'm saying less than or equal to, greater than or equal to, which means I'm saying it's one or the other, but not both. Okay, one or the other, but not both. So law of trichotomy, we will see this used quite often, especially when we approach proof in the future. We'll be looking at trying to compare quantities, and if we know that we have a certain comparison of quantities, we know that must be the precisely one of those comparisons that holds true, either equal, less than, or greater than in comparing those three quantities. Well, with that, that's the end of the introduction of our algebraic postulates. We'll meld these algebraic postulates in with our geometrical postulates as we approach reasoning. So with that, make sure you're looking at the 1.5 worksheet on the algebraic postulates. You will not only use the algebraic postulates on the worksheet, but you'll also be using some of the geometrical postulates as you begin seeing some of those melded together. If you do have any questions on this, please do not hesitate to contact me. Send me an email, I'll get back to you. With that, be good and do good.